Hi everyone. So, as a reminder, we finished our previous lesson talking about the takeoff run and the factors affecting the takeoff run. So, the takeoff run, as you remember, was the section during the takeoff from the brake release point until the liftoff has occurred. So, the factors we mentioned that affect this takeoff run were the mass of the aircraft, and the density, which we broke down to the pressure, altitude, and the outside air temperature. Also, of course, humidity. And basically this is where we left off. Of course, we also mentioned the runway surface a little bit. So runway surface. So, the next important or major factor is going to be, which we haven't really touched on, is the so-called engine bleed air system. So engine bleed air. Without going into the fine details of this system, just as a very, very simple basics, what you have to understand is that there are a whole lot of systems in the airplane which require high pressure air to function, basically. One of them, which is very convenient for us, is the air conditioning system, just as an example. So basically what they do, but another example where they would use this bleed air, so one would be the air conditioning, where they would use high pressure air. Of course, as we discussed, as with the altitude increasing, the outside air pressure decreases. So for the human body to basically be able to function normally, you need a high pressure air, and they get this from the engine. And also for the de-icing purposes. So de-icing of the engine, for example. Okay, so what they do initially is that in the engine you have the compressor, combustion chamber, and then of course the turbine. So what they do is they take air, hot, high pressure air from the compressor, basically, from the compressor of the engine. So this is high pressure, high temperature air, basically, and they bleed this air into the so-called bleed air system, and then it's distributed to the different systems, and they bleed it because this pressure is then basically not used to generate thrust in the engine. So they bleed away this air. So bleed air. It's not used for thrust generation as it's originally intended. So anytime basically you have these bleed air valves turned on, or the bleed air on, as we say, you bleed air away from the engine, and therefore it has a similar effect as to increasing the pressure, altitude, or the outside air temperature. So let's say initially this was your thrust curve. So you have thrust and velocity. So for the jet, you remember that, let's say this was your thrust available. This is your thrust with, for example, air conditioning on, air conditioning off. And when you turn on the air conditioning, so you bleed air right here, air away from the engine, therefore this thrust curve reduces, right? So our thrust, air conditioning on. And this is what we have to remember. A way this is also phrased, usually later on in the Class A diagrams, is with saying that the air packs or air conditioning is turned on. So you will have to know by default that when the air packs and the air conditioning is on, that will reduce the thrust which is available to the aircraft, basically. And that's what you have to remember. Just as an example, at Wizz Air, for both the takeoff and landing, it is in the standard operating procedures to turn off the packs. So basically for that time they turn off the air conditioning to give the engines basically, and therefore the aircraft, the most performance available. But altogether, what we started discussing it initially for is the takeoff run. So of course, if you have the air conditioning turned off, the takeoff run will decrease, right? That is beneficial for us. So if the air packs and air conditioning is on, in that case, your takeoff run is going to increase, which is bad for us, and that's the effect. Okay, so that was one of the things which we needed to talk about. The second one, which we partly touched on, is the effect of wind on the takeoff run. Okay, so simply speaking, this has already been mentioned, generally speaking, but let's just go through it again. So basically here you have your little airplane, and we also gathered the forces acting on this little airplane. So in the center of gravity, we mentioned that we have the thrust acting in the longitudinal axis, you have the lift, you have the drag, and you also have the weight of the aeroplane, right? And you also have the reaction forces. You have the reaction forces in the wheels. So you have reaction force 1, reaction force 2, and you also have the friction forces at both wheels, because you also have the friction, right? And so what wind achieves for us is that the aerodynamic forces, especially the lift, but also the drag, as we will see, is of course a function of the true airspeed squared times the rest of it, times the surface, and so on and so forth. So we will see that if you have basically a headwind, component, basically you will reach the true airspeed where the aircraft needs to reach the liftoff. And remember that the takeoff run is the distance between the brake release point and the liftoff. And the liftoff is defined as a true airspeed, right? So if you have a headwind, you will reach the liftoff speed at a shorter time, basically. And so distance is velocity times time. And in this case, the takeoff run would be a ground speed times the time it takes for you to reach from the brake release point the liftoff. And therefore, we're saying that if you have a headwind component, this time reduces because you reach this speed earlier, because you already have a headwind component, and you're also going to have a a smaller ground speed altogether, but the time basically it takes for you to reach this VLOF is going to decrease. So altogether, the takeoff run is going to decrease. And so basically you will reach liftoff at a lower ground speed as well, and at a shorter amount of time. And this is sort of the caveat. Okay, and if you have the contrary, if you have a tailwind component, everything happens in the exact opposite way, right? So if you have a tailwind component, what happens is that you reach your true airspeed where you need to lift off at a higher ground speed, right? So if you reach your liftoff true airspeed at a later ground speed, your ground speed is going to increase, and your time it takes for you to reach this speed is going to increase. Therefore, your takeoff run is going to increase. So we can clearly say, even if it takes the same amount of time for you to reach the liftoff speed, which it doesn't, but if we considered it did, even the difference between the ground speed would give us the same effect. So we can say altogether that if you have a headwind component, your takeoff run is going to definitely be reduced. And if you have a tailwind component, your takeoff run is going to increase. And this is why it's stated later on in the EU ops that for flight planning purposes, so in EU ops, it is stated that the mandatory factor of the wind when determining takeoff distances for public transport flights. So for public transport, or how we have called it is CAT, is a commercial air transport or public transport flights. It's basically using no more than 50%, so maximum 50% of the reported headwind component and no less than 150% of the reported tailwind component. So minimum 150% of the reported tailwind component. And I think it's very obvious that this also is going to basically include a safety factor, because let's say that you have a 10 knot headwind, right? And you have calculated your takeoff run with this 10 knot headwind. But as you will see, in reality, wind is not this constant. So of course there's going to be changes in the magnitude and also in the direction of the wind. So either of these changes is going to lead to a difference in the actual headwind component. So if you've done your calculation with the reported headwind component, so in this case, or in this example, 10 knot, and you can barely make the takeoff run, so you marginalize the situation, and in reality, let's say you have an 8 knot tailwind, an 8 knot headwind component. In reality, what it means is that your takeoff run is going to increase compared to the 10 knot headwind situation, and therefore you will not be able to make the takeoff run, right? But according to this rule, it says that the maximum amount that you're allowed to take into consideration when you do the calculation is 50% of the reported headwind component. So if you have, for example, 10 knots of headwind, you're only allowed to take into account 5 knots into the calculation, and you can do your calculation for the takeoff run with 5 knots of headwind. So in reality, you have like a 50% buffer in your calculation. So as long as the actual headwind component doesn't go below 5 knots, you should be able to achieve your takeoff run. But we will also see that there's gonna be a buffer in the takeoff run calculation, so they're not gonna let us use, especially for commercial air transport or for public transport flight, the entire takeoff run available. So there's going to be a buffer in that. But even if they did, just from the wind's point of view, there's a 50% buffer in the headwind. And the same thing happens for the tailwind component, right? So if you, let's remain at the same example. So you have a 10 knot tailwind. You have a 10 knot tailwind, and you do your calculation, and you can barely use the entire takeoff run which is required. So let's say that you now have 12 knots of tailwind. In that case, if you did your calculation with a 10 knot of tailwind and you barely could make the takeoff run, if you have now 12 knots of tailwind, in that case you're not making the takeoff run, right? And it could happen, right? So there's a change in the actual wind direction, or there's a change in the magnitude of the wind. It's very possible. This is why in this scenario, if you have a 10 knot tailwind, you have to take into account at least, so minimum 150% of the reported tailwind. In reality, we're going to do the calculations exactly with the 50% and the 150% rule. But in reality, you could say that for the headwind scenario, you take still air conditions into the calculation, right? Because that's still within the maximum 50% reported. And in the minimum 150% reported tailwind component, you could say maybe that you're going to take like 200% of the reported tailwind into account because you can do that. But of course, you don't want to oversize the safety factor, because you guys remember the example with the chair. So safety factor costs money, and it's ineffective to have high safety factor. So therefore, we're not really gonna do that. Okay, so you might also say like crosswind limitation. So we will consider that crosswind has no effect on the takeoff run, but in reality it's gonna have an effect. So in reality, as you can imagine, having a crosswind, especially like a more pronounced crosswind, is going to require during the takeoff to use your ailerons. So that's going to increase your drag, and therefore altogether, if you guys remember, like the acceleration along the longitudinal axis during the takeoff run was the thrust minus the aerodynamic drag minus the sum of the friction forces over with the mass of the aircraft. And it's very visible that if the aerodynamic drag is going to increase, right? If the aerodynamic drag is going to increase, basically the acceleration is going to decrease, and that means your takeoff run in reality is going to increase. However, we don't take that effect into account for the performance takeoff calculations, basically. But in reality as well, there is also always a crosswind limitation for the aeroplane, and the reported crosswind component cannot exceed the crosswind limitation of the aeroplane. Okay, so in general performance calculations, you can find examples where the wind is not given like an exact like value. Like it's not gonna say okay, today the wind is headwind 5 knots or tailwinds 15 knots. So it's not always going to give you the headwind or tailwind component right away. But what they might say, and this is our next area, which you guys have already covered, but let's just do like one example so that we also discuss it. So basically what we're going to talk about is calculating the wind components. So wind components based on the reported wind and the runway direction. Okay. So the first thing first. Usually in the reported wind, let's say in the example, they're gonna say wind is 350 degrees, 15 knots, and the runway direction is, or they're gonna say you're taking off from runway 31 left. Okay, so what does it all mean? Usually, how to solve a problem like this, from my recommendation, especially initially, is to just draw a compass, right? So this one, you're gonna have like the magnetic directions on the compass, right? So you have 360 degrees, 090 degrees, 180 degrees, and 270 degrees, right? So this would be, of course, north, east, south, and west. And you can start from, let's say, the middle of the the cross basically, or of the compass rose. And here it says runway direction is 31 left. So what I'm interested in is usually not even the designation, the left, right, center, which just means if you have two parallel runways, for example, if you have two parallel runways, the one on the left landing from this direction would be indexed as left, and the one on the right from the landing or taking off direction would be right. And of course, from the other side, this would be the left, and this would be the right direction, where you're coming in from this direction, right? So the designation is this what it means in real life, but in performance, it's not going to have any significance at all. However, this part is more important, the runway direction. So what we do with this number is we multiply the runway direction number with 10, and in this case we get 310, and this will be the magnetic direction of the runway. So 310 degrees, right? And this would mean that the runway is pointed in 310 degrees. So that's approximately like 40 degrees from west. So if you add to 270 40 degrees, that would just look something like this. So approximately to this direction you would have runway or direction 310. And around it you can initially even draw a little runway. So you would be taking off in this direction. Okay. So just to remember the direction of the runway. So runway 31, if you multiply it by 10, it gives you basically the runway's direction, the direction in which the runway is oriented from the direction of the takeoff or the landing. It's what it means. So in the direction you would be facing when you take off or land from a runway. And very importantly, the reported the reported wind component, this one basically tells you the direction from where the wind is coming from. So 350 is just 10 degrees from 360. So 350, and the wind is blowing from 350 degrees. So let's have a larger vector. Let's say that this would be your wind, and the magnitude is like 15 knots. Okay. So we can already pretty much tell that when we're taking off in this direction, right? When we're taking off in this direction, I'm gonna have a headwind component and a crosswind from the right. It's kind of visible, but if not so, don't worry, we're going to break this whole thing into components. Okay, so we're gonna break this down to two vectors, basically. So what we're gonna do is we're gonna take from the tail of the vector, we're gonna pull a perpendicular to the runway direction. And we're gonna break this vector into two components. This one, which is going to be the crosswind component from the right. And we also have to have another vector, some in the other direction, let's say like this. All right. And we can tell that the angle between the runway direction and the wind is basically the 350 degrees minus 310 degrees, right? Does that make sense? So basically you're looking at this smaller angle, right? This angle right here. And this angle is going to be between direction 350 and 310, and this is going to be 40 degrees. Okay, So how do I calculate the magnitude of this vector component? So the way I do that is basically with the help of the sine function, right? So what I'm going to say, I'm going to magnify a little bit so that you guys can see it. So I'm going to say that the sine of the 40 degrees right here, and actually before we do that, let's just give it a name, this one. Let's say this is actually the wind would be W vector. This would be the crosswind, so WX, and this would be the WH for the headwind component. Okay, so let's get back to this one. So sine of 40 degrees would be the opposing side, so this is the opposing side, right, over the hypotenuse of the triangle, so this one, the 15 knots. Okay, so sine 40 is the WX over 15 knots, right? So therefore, from this one, I'll just take it over where I have more space. We can calculate the crosswind component is going to be the sine 40 degrees times the 15 knots, which I'll just calculate in a second with the help of a calculator, hopefully. So sine of 40 degrees times 15. If you do the calculation as well, it's going to be approximately equal to 9.64, so 9.6 knots of crosswind component. So this is going to be your crosswind component from the right. And we're also going to calculate next the headwind component with the help of the cosine function, right? So the cosine 40 in this case, right? So how can you calculate the cosine of this angle? It's basically going to be the adjacent side, so this one, right? So this one over with the hypotenuse, which is the 15 knots, right? So the WH, the headwind component, over with the 15 knots. So therefore, we can go ahead and say that the WH, the headwind component, is going to be 15 knots times the cosine of 40 degrees, which is equal to 15 times cosine 40. It's basically 11.49, so 11.5 knots, right? And this is the one which you would take into account, right? So you would say that the headwind component for this takeoff is going to be 11.5 knots. And so my question is, for this calculation, so if they give you like runway 31 left, wind is from 350 degrees, 15 knots, what is the maximum amount of headwind component which you would take into account for a commercial air transport flight? What is the maximum amount? If you remember what we discussed previously in EU ops for commercial air transport, so this rule right here, we said that for reported headwind component is going to be the maximum of 15% of the reported headwind component, and if you have a tailwind, you have to take into account at least 150% of the reported tailwind. And of course, we have a headwind component, so therefore it is the maximum 50% of this reported tailwind component. So for this case, it's going to be 5.75, which you would take into account for a commercial transport flight. So one do note here with the reported winds. So usually we're going to be using them for takeoff gradient calculations, but the charts, any chart basically which includes winds, and this is going to be most charts, most performance charts. So for the takeoff distance chart, the landing distance chart, so basically the accelerate stop distance chart, all of them are going to include wind information, and luckily, the performance charts have this included, and we're going to see exactly how when we get there. But I just wanted to say that when you do a performance chart, basically, always remember that this rule doesn't apply, because in the performance charts, in the performance charts have this already included. So if you're given, a 10 knot headwind component in an exercise for a performance chart, you don't have to calculate with 5 knots, you just simply calculate with the 10 knots. You can directly input that into the chart. You don't need to take this rule into account, is what I'm trying to say. Okay, so, but for this exercise we had to. I would just advise you guys to do at least few of these calculations so that it becomes more and more automatic, because it can, as you can see, it takes quite a few steps, and it can take up quite a little bit of time if you don't have a lot of experience with it, even if you know how to calculate the right angle. So you can make up any runway directions, any reported winds, and just do the calculation. Initially, I would advise to draw it up just like the way we did. Draw up the compass, the runway direction, and the wind, and from there you can draw up the vectors. And I think from there it's very visual. You don't have a hard time calculating it, and after a while it's going to become more and more automatic, and you'll be able to visualize it easier. That would be my advice on that, because yet again, it can take up a lot of time, and you're not going to have a whole lot of time on the exam. So this is only like one step of the entire calculation, and you're going to have to do the whole chart itself, and and time is very limited. Okay. So the next area we're going to talk about briefly is the effect of runway slope. So runway slope is also going to have an effect on takeoff. So runway slope. We discussed briefly in our last session the effect of slope, but let's go through it again. So when we initially talked about the takeoff run itself, we presumed the runway to have absolutely no slope. So in this case, we're going to start with an upslope. So in case of an upslope, you're going to have an inclined runway. Like, we're of course over exaggerating right here, but so here's the runway. And let's say we also have here a local horizontal, and we can even define like an angle between the two, which we're just gonna call, like, let's call it major phi. Okay, so we're gonna have an aircraft on this whole entire thing. We're gonna have an aircraft right here. That's right here. Okay, and this aircraft is gonna have hopefully a center of gravity and the longitudinal axis, which is the x-axis, and it's gonna have a z-axis, right? And these are the axes of the aircraft. And it's also going to have a local vertical axis, right? A local vertical, along which the gravitational acceleration acts. Actually, let's draw this a bit further so it doesn't disrupt the image itself. Okay, so we're also going to have a undisturbed airflow vector. We're going to say that this undisturbed airflow basically has like three components of Vx, Vy, and Vz. And we're going to presume that this undisturbed airflow is only flowing in the negative longitudinal direction with this with the magnitude of V and no other components, right? So in this case, we can say that the lift force is basically going to be perpendicular, so acting in the negative z direction of the aircraft. So here you're going to have the lift force you're also going to have the drag in the negative longitudinal direction. You're also going to have a thrust force, and you're also going to have a weight, right? So here you have the weight of the aircraft, and let's not forget about the reaction forces. So reaction 1, reaction 2, and therefore an effect of these reaction forces and the movement of the aircraft. You're going to have the friction force 1, and you're going to have friction force 2. Okay, but what's more important is that if we want to sum up the forces acting on the aircraft, we can see that the weight doesn't fall into either the longitudinal nor the vertical direction, right? So we're gonna have to take it or break it into two components, just like we did with the climb, for example. So we're gonna have a perpendicular to the vertical axis, and we're gonna have, well, the color is not very visible, so let's choose another one. So we're gonna have a weight component. We're gonna have a weight component in the vertical axis. Let's call this WZ, and we're gonna have a component of the weight acting in the longitudinal direction, and we're going to call this WX. Okay, so I think you can already see how these two components are going to be calculated. So because we have a perpendicular here and we have a perpendicular here, this phi angle is going to basically equal this phi angle up here, and from there the calculation is fairly simple. So if we look at the cosine of phi, basically is going to be the adjacent side, so the WZ component over with the hypotenuse, which is the weight. So on the WZ component over with the weight. So therefore the WZ is going to equal the weight times the cos phi, right? This one. And we can calculate the WX component with the sine of phi. So sine of phi is going to basically equal the opposing side over with the hypotenuse. So opposing side is the WX component over with the hypotenuse, which is the weight. So therefore we can go ahead and calculate the WX is going to be equal to the sine phi times the weight of the aircraft, and there you have the second component. And if you want to sum up the forces which accelerate the aircraft in the longitudinal direction, you first have to look at the vectors, or basically the sum of the forces acting in all directions. So let's look at some of the forces acting in all directions. So because this is a three-dimensional one, we're going to have some forces in the x direction, some forces in the y direction, and some forces in the z direction, right? And let's start with the sum of the forces in the x direction, this one. So sum of forces in the the longitudinal direction include basically the thrust in the positive direction, and in the negative one you have the drag. You have the sum of the friction forces, where the sum of the friction forces would be basically the friction 1 plus friction 2 plus, you know, how many frictions you would have. So it's just basically summing of the frictions on the wheel. Okay, minus, and this is what's important, is that compared to the level runway condition, we also have this component. So basically the sinus of the phi times the weight of the aircraft. And if you remember how we call this component, we call this the weight apparent drag, right? So the weight apparent drag. weight apparent drag. And this is an extra component based on the previous ones. And we could also do the sum of the forces in the y, which we're going to presume for this calculation to be 0, and we could also do the sum of the forces in the z direction, but you know, it's not important. So what is important, or you can actually like do it and see how the whole thing is affected. You're going to see that the friction forces are actually reduced somewhat because of this reduction in the weight component. But what is more important is the, of course, the acceleration is basically the acceleration in the x direction, the acceleration in the y direction and the acceleration in the z direction. And the acceleration in the x direction can be calculated as the sum of the forces in the x direction over with the mass of the aircraft. So therefore, these about, you know, we don't care right now. So the sum of the forces in the x direction, we said, is the thrust minus the drag minus the sum of the friction forces and minus the sinus phi times the weight of the aircraft over with the mass of the airplane. So right now we have an extra component which altogether, if the thrust remains the same and if the drag remains the same and the sum of the friction forces, which in reality is going to be reduced a little bit, but we can see that the this component, this weight apparent drag, is going to increase a whole lot. So therefore the entire fraction is going to reduce the entire expression, because the mass is going to be considered constant for this calculation. The entire acceleration is going to be reduced, right? And if the acceleration is reduced, therefore the distance in which we can cover or accelerate to from the brake release point to the liftoff is going to increase, right? So if we have an upslope, in that case, we're going to have an extra component of the weight acting in the drag direction. So this one is what we call the weight apparent drag, and is going to be added to the drag side of the equation, right? Because remember, like thrust minus the sum of all this, the sum of the drag plus the friction forces plus this weight apparent drag is we call the sum of the drags, and the thrust minus the sum of the drags we call the excess thrust. And so this whole excess thrust is going to be reduced, and therefore the takeoff run is going to be increased, right? And so this is the altogether effect. So if you have an upslope, your takeoff run is going to increase. And so just very briefly, without going into the same amount of detail as we had, so if you have a downslope, what happens? So if you have a downslope, the whole thing like changes, right? Because if you have a downslope, here you have the local horizontal, here you have the phi angle, right? And yet again, like we're over exaggerating very much right here, but we have the longitudinal axis of the aircraft, we have the vertical axis, and we have the airplane in its entire majesty right here. There's also a pink one. Okay, so basically we're gonna have the lift, we're gonna have the drag, which we can presume everything is the same, and we have the thrust, and we have the weight. And this is what's gonna be interesting, is that the weight is gonna be breaking into two like components yet again. Oh, sorry, this is not the best color. Let's have this one. So this one would be the cosine phi times the weight. This one below, so this one would be the sine phi times the weight. And so therefore we could see that the sum of the forces in the x direction would be equal to, just one second, the sum of forces in the x direction would be equal to the thrust plus, because this vector, this one right here, is pointed the same way as the thrust is doing, so plus the sine phi plus the weight, or times the weight, and minus the drag, and minus the, of course, the friction force 2 and the friction force 1. Right, so the sum of the friction, basically. So minus the sum of the friction. And of course, from this, just like in the previous case, we can say that the acceleration in the x direction is going to be the sum of the forces in the x direction over with the mass of the aircraft. So therefore, the thrust plus the sine phi times the weight minus the drag minus the sum of the forces, sum of the friction forces. So therefore, we can see that the higher the downslope, the bigger this downslope, the bigger the sum of the thrust plus the sine times phi. And so therefore the entire excess thrust is going to be larger, so the entire, of course, if the mass is a constant, then the entire fraction is going to be larger, so therefore the acceleration is going to be higher. So if you have a downslope, your takeoff run is going to decrease. And this is the final effect right here, which we have to remember just for the takeoff run. Okay, so if you have an upslope, your takeoff run is going to increase, right? Your takeoff run is going to increase because you have the weight apparent drag. And in case of the downslope, this component, this weight apparent thrust, in this case we could call it, is added in the direction of the thrust, so to the thrust part of the excess thrust, and therefore increasing the acceleration, which decreases the takeoff run, which is required, because we can accelerate that wheel-off to the lift-off speed from the brake release point in a shorter distance. And that's it for this lesson. This is where we're going to call it. In the next one, we're going to continue with the runway surface on the takeoff run and the use of flapper, basically the effect of using the flaps on the takeoff run, and how this is going to give us the optimum mass for the takeoff run. Okay, so thank you for your attention.